Hello everyone and welcome to the next lesson of the School of Solana Season 7. This lesson is going to be about Solana Programming Model Part 1, and yes, there will be also Part 2. In the Part 1 you will learn, or we will talk about accounts on Solana, programs on Solana, and also transactions on Solana. And in the Part 2 we will talk about, for example, cross-program invocation, which means execution of different Solana program from your Solana program. And we will describe also, for example, program-derived addresses. So if you struggle to understand PDAs on Solana, I would definitely recommend you to watch also the Part 2. I hope that you are enjoying the School of Solana, because we are definitely enjoying it. We can see that there are a lot of discussions on the Discord, so that's pretty nice. We hope that you are enjoying our AI agent, which we think can be really helpful due to its knowledge. And yeah, that said, I would say we can continue directly to the lesson. So enjoy. Firstly, I would like to talk about the overview. So I would like to talk about how it works in general on Solana. And then in the overview, we will talk about the terms such as transactions, programs, accounts. So we will describe these. But firstly, I think it is important for you to understand how it actually works, starting from the point where you as a user interact, for example, with Phantom app, to the point where the instruction is executed on the Solana network. So it starts with an app interacts with the Solana cluster by sending it transactions. Transactions can contain one or more instructions. The Solana runtime passes those instructions to programs deployed by the app developers beforehand. That means you as an app developer creates Solana program, then you deploy it to the desired cluster, so for example DevNet, or if it's in production then mainnet, and then other users can interact with your app by sending it transactions, by sending transactions to the Solana cluster, that means to the mainnet, for example, and the transaction contains the instructions which are meant to call your program. I will talk about the deployed program later in the program section, but in order for you to have a basic idea, you as a developer of Solana programs, you create a program and then you deploy it to the cluster. That means at the end, all of the validators, as I said, the Solana is globally synchronized state machine. All of the validators have synchronized state. So each validator software contains your Solana program when it's deployed on the desired cluster. That means other users can interact with your program, for example, by sending the instructions which are wrapped in transactions. But we will see this later on in more details. What is also important is that instructions are executed sequentially and the transaction is atomically evaluated. That means if transaction contains multiple instructions, that means the instructions are executed one by one, and transaction cannot have state like in the middle. It on one side can successfully pass or return an error due to error in one of the instructions. If any instruction in transaction fails, then all of the changes that were so far made by, for example, different or other instructions in the transaction, then all account changes are discarded or reverted. So this is the basic idea. This is the overview of how it works on Solana. So it starts with the app. The app creates the instruction or multiple instructions. These instructions are then inserted into the transaction. This transaction is, for example, signed by you as a user if it has to be authorized by you. And then the transaction is sent to the Solana network or to the one of the Solana validators. And there the execution actually occurs. So this is the overview in general. Program is a piece of code that is deployed or in brackets included to and runs on the node. So I have specified validator here, but we were also discussing RPC nodes. So that means you create a Solana program in Rust, then you compile it and you have the binary file, and then you can deploy this binary file to the validators of the desired cluster or nodes of the desired cluster, and then other users can interact with your program. The Solana programs are similar to regular Rust binaries. So as you could see in the previous lesson, we were discussing Rust source code, and you could see that the Rust source code contains, for example, a main function, which is like entry point to the program, and the behavior is similar on the Solana blockchain, but there it is not called main function, but it is called entry point. So if you specify your Solana program in such a way that it supports multiple instructions, you cannot directly call the instruction or the function of the program. You will see this in the hands-on example. But you need to specify data and create the program in such a way that it can dispatch the data and call the desired function. So that's why it is called entry point, because this entry point is always invoked by the Solana runtime. So the runtime does not invoke any particular function that you have specified in your Solana program, but it always invokes this entry point. Programs are stateless, meaning you can't store any data in them. This means that yes, you can have, for example, variables in your Solana programs, but if you want to store actually data somewhere, you need to store them in accounts. So we use accounts to store both programs code and also data. So once again, you as a developer create Solana program, then you build it into binary file, which is the file with the name .so, and you take this binary file and deploy it to the desired cluster. This can be really easily done by the Anchor framework, as you will see. And then if it's deployed, then it does not have any state, the program I mean. So that means the programs are stateless. So in order for programs to store data, they store the data in accounts. And you can imagine accounts as a files. Each file have its own address, which is unique and stores data. And if you would like to read some of the data in your program, you need to specify from which file you would like to read the data from. But you will see this in the accounts section. So we can continue directly to the account section. On Solana, everything, all data, all programs or wallets are stored within accounts. So you may already heard this, but it is always said that on Solana everything is account. And it is true. So everything is account compared, for example, to the everything is file. Think of it as a key value pair. So for example, in Rust, it is called hash map, but this is just an example. I wouldn't like to straight compare it to the hash maps, but just an example. So as hash map contains key, which is unique, and then for the unique key, it also contains the desired value. Same goes for the Solana. So each account has its desired individual or its desired key. This key is your public key, and each public key has its own account. That means you can see this as the key value pair or hash map. And this database is stored in the validator. So when you try to invoke or call some of the programs that are already deployed in the cluster, as I said in the overview, you create transaction which contains instructions. These instructions have actually specified by you as a developer of the program which accounts to expect on their inputs. So on the off-chain side, where you actually create the transaction, you need to specify all of the expected accounts. And then, finally, the program, when the transaction is sent to the cluster, then the program can work with these accounts. So similarly, if you specify, or if we take the analogy with the files, it is like invoking some program in your computer, and the program has specified which files it has to read in order to work. So you need to include these files on the input of the program invocation. So, and same goes for the Solana. As I was talking about the key value pair, so the address of account, so from the analogy, the key is the 32 bytes long public key. So for example, you can, if you have Solana wallet, which you probably have as you are registered to this School of Solana Season 6 with the Solana wallet, then your Solana wallet has also public key. So you can look at it really similarly, that your account would be also stored in this database of accounts, but your account does not actually store any kind of data. For example, only balance, if you have any Solana in your wallet. But there are also different types of accounts that store the programs, that stores the data to programs. Now you understand the key part of the key value pair. Let's now talk about the value part. So the first thing, you can see the data. So data is a byte array that stores data. If the account is a program, this stores executable code. So if the account is program, this stores executable code. If the account is not program, then this data field stores actually the data that the program needs to store or wants to store. So these are called data accounts. Then you have the executable flag, which is just the boolean to indicate if the account is program or not. Next, you have LAMP ports field, which tells you how many LAMP ports the account has. And then the owner. Owner specifies the public key or program ID of the program that owns the account. In the next slide, this is going to be important information. So we can just go to it. Accounts can store up to 10 megabytes of data, which can consist of either executable program code or program data. Accounts require a rent deposit in Sol. That means if you want to store data in account, you need to deposit also some amount of Sol, or let's say LAMP ports. So you are actually paying for storing the data on chain in the data account. If you pay more than 2 years of this rent, then the account is called rent exempt. So that means you need to pay this amount only once, and it is not paid regularly, but only once. And also this rent exemption is refundable. That means if you initialize data account with your program, then you decide that you would like to close the account, then the rent is refunded to you. And regarding the owner field, every account has a program owner. Only the program that owns an account can modify its data or deduct its LAN ports. So let's talk about the example. You have Solana program. You know, as I mentioned before, programs are stateless. That means when the program is invoked once by any user, and then after, for example, 1 week, it is invoked second times by second user, the program has reset its state between the invocations. So it has to store the data somewhere. That's why we have data accounts. And this point is talking about the fact that these data accounts can be modified only by the program that owns the account. That means if you have the Solana program, you as a developer created program that has some particular logic, and you would like to store data in some data account. This data account will have its owner field set to your program. That means this data account can be modified only by your program. What might be important here to mention is that anyone can increase the balance. So if you decide to send LAN ports to the data account by whatever reasons, you can, but you cannot deduct its LAN ports. I mean, you as a random user. If you would like to deduct its LAN ports within the Solana program that owns the data account, then you can. Then the second part, programs are stateless accounts that store executable code. So yeah, already third time, but it will definitely help you to understand it better. Programs are stateless, so there is no such thing as stored state in program between invocations. If program wants to store the data somewhere or the state somewhere, it needs to store it in the accounts. In particular, in the data field of the account. You will see everything in the hands-on example or in the basically in the programming examples. Data accounts are created by programs to store and manage program state. So this is basically what I said just now. And then you can have multiple types of programs. So let's call these programs, which are created by developers, let's call them custom programs. Then you have for the second type, which are called native programs, and these are built-in programs which are part of the validator implementation. So for example, you can have system program, and this system program is actually really important because your Solana wallet is owned by the system program, and if you want to transfer Solana from your wallet to wallet of your friend, you under the hood, or the wallet app under the hood needs to create transfer instruction for the desired amount of LAN ports you would like to send. Then it is inserted into the transaction, and then the transaction is signed by you, and the transaction is sent to the Solana cluster, so mainnet. But you do not maybe know this because you are just the user of the wallet app, so you just click on the send, you enter the desired amount of SOL, and you just sign the transaction, and that's everything. But under the hood, it invokes the system program transfer instruction. Then you can have also, for example, the BPF loader program, which is the owner of all other programs on the network. So in this case, as I said, we have the custom programs that are created by the developers. So the BPF loader is owner of these custom programs. Last but not least, we have sysvor accounts, and these accounts are special accounts that store network cluster state. So for example, we have clock sysvor account, which contains cluster time, synchronized cluster time, so every validator has the same state of clock account. So in summary, you can see in the picture from left side to the right side, it starts with the BPF loader. As I said, this is the owner of custom programs. So BPF loader is owner of program. This program is actually stored in the account, and you can see that the data of account actually consists of the program code. Then you have the executable flag, which is set to true, as this is executable program. And you have some particular number of LAN ports also here, and you have specified once again the owner, which is BPF loader program. Then you want to store some desired data, some desired state, let's say it, but programs are stateless, so better, some desired data. So your program is going to be owner of data account, and in this data account, you can see the owner is your program. The LAN ports are not exactly the same, but the idea is the same. What is different is the executable flag, which is in this case set to false. And what is also different is the data field, which is program state. So for example, you will see this in the examples. You want to store some data, you store it in the data accounts. So you store the state there. That was all from the accounts, and now I would like to move to the transaction. Transactions are sent to interact with Solana network. This one sentence, I would say, describes everything about the transactions. Yes, there are more details that you can learn about transactions. They contain some metadata and some other fields that are required in order to be processed by the Solana network. But in order to understand how actually the Solana works, it is this easy. Transactions are sent to interact with Solana network. Then the transactions contain instructions. These instructions can be executed by Solana programs. So user or app sends transactions to Solana validator to interact with programs deployed in the validator. Just to clarify, why do I have the user or app? So for example, if you have Phantom wallet and you are just the normal user of the wallet, what is happening under the hood is that the Phantom actually creates the transaction, then or system program transfer instruction, it adds it to the transaction, then you sign the transaction. But this everything happens under the hood. You as a normal user of the Phantom wallet, you just click on the send, and then you sign the transaction, or before that you enter the desired amount that you would like to send. Then you sign the transaction, and the LAN ports are sent, or the Solana is sent. But the second option here, as I have specified also the user, you can do this also as a developer. You will see this in TypeScript code. It is really easy. Just, I would say, 10 lines of code. You can create new transaction, add the system program transfer to it, and you can basically transfer funds between users. So yes, it is this simple. Transactions include one or more instructions. The execution logic for instructions is stored in programs deployed to the validators. So as I was comparing programs or Solana programs to the Rust binaries, when you have the main function in normal Rust code, this is the entry point to the program. This function is invoked at the start of the invocation of the Rust program. If you have Solana program, it is pretty similar. It is not called main function, but it is called entry point. And again, this entry point is executed or called every time by the runtime. This this entry point function contains some parameters, and based on these parameters, you as a developer needs to create logic that each instruction that invokes your program needs to be dispatched correctly or the logic needs to be implemented correctly. It may sound like really difficult to create such stuff as a developer, but you will see it is actually really simple with the Anchor framework. Then the execution order of instructions. So yeah, instructions are executed sequentially. So from the picture, for example, you can see the right transaction contains 3 instructions. So the execution is that the first instruction is executed, the second and the third. If, for example, the second fails, then everything is reverted and no changes are made. What do I mean by no changes are made? As I was talking about the accounts, so for example, you have data account and the first instruction actually modifies some data in account. Then the second instruction fails. That means the updates that were made to the data account in the instruction number 1 are reverted. Atomicity of transactions. So again, really simple concept. There are 2 options. The transaction or all of the instructions in transaction passes successfully, or one instruction returns error. That means everything that or every change that was made in the transaction, all the changes are reverted. Now let's have a look at this example. So again, from the left side to the right side, then to the middle. So it starts, this is example of the transferring LAMP ports with the system program transfer instruction. So let's start with the sender wallet account. This account does not contain any data, it is not executable, it contains some amount of LAMP ports, and the owner is system program. Then the sender decides that he wants or she wants to send her or his friend some amount of Solana or some amount of LAMP ports. So the sender signs and sends the transaction. So this is as from the example of the Phantom wallet, you click on the send and you sign the transaction. You can see the transaction on the right side containing the transfer instruction. This instruction actually invokes the system program. This system program contains transfer function. It has to correctly dispatch the inputs, because also system program has its own entry point, and the transfer function actually updates the LAMP ports in the sender wallet and also in the receiver wallet. You can see this is indicated by the arrow pointing down or arrow pointing up in the LAMP ports field of the sender or the receiver. And I was talking about the key points in the accounts, for example. So, and there was a point that only the account owner can modify the account fields. So this is a great example of that. You can see the owner of both of the accounts are system program, or is system program. That means the transfer instruction can actually modify the LAMP ports, because the transfer instruction is contained in the system program, or the transfer logic is contained in the system program. Then the system program is owner. That's why there was also a point about the adding LAMP ports, that it can be done by anyone. But for example, the subtracting LAMP ports cannot be done by anyone, but only by the program owner, or in this case, the owner field. That means the system program. I want to describe it to you as good as possible, but I understand that some concepts might be really difficult for you, but when you learn it, you will see that it is really, really simple. And now I would like to show you a quick hands-on example before jumping to the Anchor. And as I said, not only the Phantom wallet can create, for example, the system program transfers, But also you as a developer or you as a user can create such logic in TypeScript code. So you can see in the code snippet, I will show you this in the Solana playground. You can see the URI to the playground, but you can also scan the QR code. But let's just now stay in the pseudocode, or sorry, this is actually from the code. So let's just focus on the code, and then we will have the hands-on example. So the first thing, define the amount that you would like to transfer. So in this case, it is 0.01 Sol. Then create the transfer instruction for transferring Solana or Lamports from wallet 1 to wallet 2, so from the sender to the receiver. So from the line 5 to the line 9, you actually create the system program transfer instruction, and you specify from public key. This is again the address that we were talking in the account section, where you can look at it as a key value pair. So this is actually the key, or similarly public key, which has 32 bytes. So you specify the from pub key, you specify to pub key, so the receiver, and you also specify the Lamport. What might be important here is that you need to convert the Solana to the Lamport. So you will see in the source code there is available constant called Lamports per sol. So you do not need to look on the Google for how much Lamports 1 sol has, but you can take the transfer amount and multiply it by Lamports per sol, which is 10 to the power of 9. So once again, just remember the transfer instruction on its inputs contains Lamport on its input, contains Lamports, not sol. Then you take the instruction and add the transfer instruction to a new transaction, which is done on the line 12. So you create new transaction and then add the transfer instruction. And lastly, you take the transaction and you send the transaction to the network. You can see you take the transaction, you have created the connection, which again you will see in the code. And lastly, you specify the sender, which is who is the signer of the transfer. Why does the sender needs to be signer? That's pretty self-explanatory, because you as a sender own the Solana. So you need to authorize the transfer to successfully pass, because if there is no authorization required, then anyone can send your Solana out from your wallet. So that's why you actually need to authorize that, yes, you would like to send the Solana. That's all from the description of the source code, and now let's move to the hands-on example in the Solana playground. All right, so you just clicked on the link, or you opened it with scanning the QR code, and you should probably see the same window as I do, as I did not make any adjustments yet. And now, for example, you don't know how to run it or what to do. So, firstly, you can see in the down left corner that we are not connected. So first thing that you need to do is to click on the settings and select from the endpoints. You can see that there are multiple options. So for example, mainnet, testnet, localhost, also custom. Just choose the devnet and click somewhere else. So make sure the devnet is selected. Now you can see that we are still not connected. So click on the not connected, and you can see that this window pops out. You can just ignore it, maybe you can read it, but for testing purposes it is alright. And click on the continue. Now you can see we are already connected, and we are connected to Playground wallet, to the devnet. You can see the address, and you can see that we have 5 SOL. If you do not have any SOL in the wallet, you will see 0 SOL here. So from my point, you can go to the wallet, and there are the 3 dots, and you can see the airdrop option, so you can click on it. But what I think is more reliable is basically open the wallet again, then we should find the copy address. So click on the copy address. This will copy the Solana address. And then go to the faucet.solana.com. Here you can request airdrop, which is more reliable option. You can also connect your GitHub, which I think brings some advantages to the airdropping. For example, you can, I think, request airdrop more often, but yeah, I'm not sure right now. I just know that the faucet is more reliable than just regular CLI airdrop. So you can see I have selected the DevNet. There is the wallet address window, so enter the copied wallet address here, and there is the amount option. So for example, choose 5 and confirm airdrop. You can see airdrop was successful, and that's everything. If you go back to the playground, you can see that in my case, I already have 10 sol, but if you had 0, you will have 5. Now let's have a look at the code. So this part selected is basically the code we seen in the presentation, in the slides. For those who don't know TypeScript, I think it is out of scope currently to describe you every line of TypeScript, but just for your info, this console.log, these are something like print ln in Rust, and then all of these lines are basically declarations of variables. So first thing that is specified here is the connection. So we are connecting to the playground connection, which is the DevNet as we selected previously. Then the sender is the playground wallet, which is generated automatically. Then the receiver is new key pair, so this will generate a new key pair for the receiver. So just keep in mind that the Solana will be transferred to the random address, not to your friend, and also it is performed on the DevNet, so you are not transferring the real Sol from the mainnet, but we are testing it on the DevNet. Then these two lines might be pretty important also for the later stages of the cohort, but I will try to also increase the size. So you can see that we have the await, connection, and get balance. So what does this mean? Is actually we are taking the sender's public key and we are trying to obtain his balance from the DevNet. So if he does not have or she does not have any Solana in the wallet, it will return, for example, 0, or if they do not have any Solana in the wallet, yeah, it will return 0. If they have any, it will return the number. Same goes for the receiver public key. Yeah, but all right. If we would like to send some Solana, we definitely need to have some balance in our wallet, so the sender public key, the sender balance cannot be 0 because we would like to send amount. So yeah, and then we have just the console log outputs. So you will see in the output what are actually the amounts in the wallets. Here is the logic that I was talking about in the slides. And here is basically the same. So the difference between here and this and this, so the code on the line 45 and the code on the line 17 is basically none. Difference is only that this will obtain balance before the transfer instruction or transfer transaction, and this will obtain balance after. That means we should see different results here as here. So we should continue with the execution. So in order to execute the code, just click on the run option here. And you can see that it was really fast. you can see that the first output is sender pre-balance, which is 10 Sol, and the receiver 0. Then you can see the sender post balance is 9.9899995, and the post balance is 0.01 in the receiver wallet. You may ask why this plus this is not exactly 10, and it is because the sender was also paying transaction fees. And yeah, I think it was in the lesson 1, I showed you the Explorer, so you can again see we are looking into the DevNet, and this is the basically transaction, or these are the transaction contents, so you can see the signature, timestamp, when the transaction happened. You can see the transaction was successfully passed. That means all the instructions within the transaction passed successfully. And if we scroll down, you can see that we have instruction field here. So for example, if we have multiple instructions in these transactions, you could see all of them here. But this time, as we have only, let me close this, as we have only the transfer instruction added in the transaction here, we can see that the transaction contains only this one instruction. And in this instruction, we are calling system program. Let me also increase the size here. We are calling the system program, and you can see that we call the transfer logic of the system program. The from address is public key, so we cannot clearly see who's the sender. Same goes for the to address, and there is the amount, so in this case it is 0.011 Sol. And then you can see the program instruction logs. So for example, if you as a developer create a Solana program which prints something into the Solana logs, you could see it here. So yeah, hopefully this was helpful. The Solana Playground is a really great tool. I'm not that used to it. I like local development more, but I definitely recommend you to try it out, and maybe you will like it more than me, and you will choose it instead of local development. So yeah, that was all from this hands-on example, and now I would like to move to the Anchor example. We are back at the Docker image that was prepared for the School of Solana. For those who still don't know where to find this Docker image, just navigate to the School of Solana repository, and within the lesson 1 there is setup section, and there you can find steps how to actually install Docker, and how to also install this created Docker image by us. More details are also in the lesson 2. You can scan the QR code here, there. So yeah, if you would like to have more details about the Docker image, just navigate to the School of Solana repository. But yeah, for now you can see that we have the empty workspace, and I would like to show you the stuff that we learned during the slides. That means I would like to share with you how actually the Anchor makes the development process really easy, as you will see that how simply you can actually define the logic, as I was talking about the entry point. So you do not need to specify the entry point by yourself and specify all of the dispatch logic, but you will see how it's done by Anchor, and you will see that it is actually really simple. So first of all, in this Docker image, the Anchor is already pre-installed, so we can create a new project called Hello World, or let's call it Hello Solana. And we call the anchor command with the init subcommand. That means we are initializing new project. Press enter. It will take some time to initialize the project. And you can see we have created Hello Solana folder by Anchor. A lot of stuff, or everything basically, is generated automatically by Anchor, but for us currently it is just enough to understand that we have this programs folder and we have this tests folder. Within the programs folder, you specify the logic of your Solana program, and within the tests folder, you write tests. For now, let me close the terminal so we have more space. And let's go just straight to the lib.rs file, which is basically, and let me reset the analyzer, stop server, maybe restart, or okay. So let's go back to the lib.rs. This is source code that is automatically generated by Anchor, and there are some important parts. First important part is this structure with the derived accounts specification. Structures like this, you can have multiple of structures like this. So for example, I can copy this and call it initialize to, for example, or update. In these structures like this, you define what accounts the instructions within your program expect on its input. So from the lesson, as we learned, on Solana, everything is account. So programs are accounts, data are stored in accounts, so basically data are accounts, and so on. System variables or sysvars are accounts, native programs are stored in the accounts. So if you would like in your program work with any kind of account from this list, from all of the types, you need to specify it in the structures. You will see in a few seconds how. But these structures, or we can call them contexts, these contains actually expected accounts. Then we have this second part, which is the main logic of the program. Let's call it the main logic of the program. This is the module name, and the most important part from my point are the functions that are defined here. Because actually these functions are instructions that your program supports. So currently you can see that we have function called initialize, which expects context, or the variable is called ctx, but the type is context with the initialize as the inner type. This initialize is actually this same initialize defined here, so this structure. And this means this initialize instruction that our program supports expects accounts that are defined within this context on the instruction input. For example, if I go and copy it, and call the second function, for example, update, and specify also the second structure that we defined here, and specified within the context inner type, that means our program currently supports two instructions, which are initialize and update. Let's compare it to the system program transfer. The system program is not written using the Anchor framework, it is written using the native Solana, or I think it is alright to call it native Solana, but it is also often referred as vanilla Solana. That means, or what that means? That means these macros actually expand to source code that we can then call vanilla Solana. So Anchor is basically, apart from other logic or other stuff that it provides, it also contains these macros that turns this source code into the vanilla Solana. But All right, I understand that this might be more difficult for you to understand, so I just want to compare this functionality only to the transfer function or transfer instruction into system program. So look at it such that if this is what we have now is system program, it would be something like transfer, something like this. That means transfer is function defined within the system program and is expected basically as instruction that the program supports. So let me let me delete the transfer. For those who would like to know more, you can go to the program, basically select the whole macro, press Ctrl+Shift+E, and write expand. You can see Rust Analyzer expand macro recursively at caret. Press enter. And the source code on the right side, this is the expanded source code from the program macro. This is, again, as I said, for those who would like to know more. It is not like crucial for beginners to understand Solana, but if you would like to know more about how it works under the hood, it might be helpful. What might be important here for you then is that there are these lines, and you can see we have something called entry point, which I was talking about previously in the slides, which is function entry point, and it expects some kind of input. And then there is the match statement, and we call entry function. If I go to the entry function, this is more readable from my point of view. The first thing is the program ID. So this field is actually program we are executing. Then we have accounts on the instruction or the execution input. We have accounts, which is array of account infos, and we have array of data. So these are 8-bit long unsigned integers, so we have byte array here. And if we go even deeper, and if we look what is invoked during the execution, so we can see that it is invoked try entry. And if we look into the try entry function, then we check the dispatch and we scroll down to the dispatch function, we can see that there is some variable initialization performed. But what might be helpful for you to understand the dispatch logic of the instructions? So basically, we take the data on this line, then we take the first, you can see, first 8 bytes of the data, and then it is called sig hash, but there is the copy from slice function, and we perform match statement to the sig hash, or we can call it, we compare the first 8 bytes of this data field, and based on the value we dispatch we perform desired logic. So this is basically the dispatch that if you do not use Anchor, you should ensure in the vanilla Solana. But Anchor simplifies this, so everything is generated by the program attribute macro. And in this case, you can see these 2 branches of the match statement. So is the first 8 bytes are equal to this discriminator value, then the initialize function is called. If the discriminator, if the first 8 bytes are equal to the instruction update discriminator, then the update function is called. So this is basically how the dispatch works under the hood, but I will close it for now because it is not that important for beginners to understand. Just keep in mind that these 2 functions, for example, you can have 10 functions there. These 2 functions are basically instructions that your program supports. All right, this is introduction to the source code generated. Let's now build the code. So we can, the source code. So let's perform Anchor build. Oh, sorry, I need to navigate to the workspace. So firstly, navigate to the freshly generated workspace. And now perform anchor build. Press enter. It will build for some time, so now we wait. All right, the program is built. So first point is that you can see that we have the target folder. This is just, again, more of informational purpose. So if you go to the target, then deploy, then you can see we have this .so file. So this is actually the binary that is then deployed to the node, to the Solana node. Then this binary is included in the account with the desired address, and users can interact with this program. So basically, when you take the binary, deploy it to the validator, then that's everything, and users can interact with your program. All right, but let's forget about this for a minute, and let's close that, and let's go to the hello solana.ts. So this is again automatically defined, or sorry, generated by Anchor, and this is basically the structure of test file. So there are some specifications such as the describe, such as the IT. This corresponds basically to the one test. I'm not the TypeScript professional, so I just know this from the previous testing experience of the Solana programs and from the experience of writing Solana programs. But yeah, you can research what these keywords mean and so on. But what is important is that on this line, we actually tell that we would like to load program from the types generated by the Anchor. So here is the import. You can have a look at this file, which is stored again, same as binary in the target, but in this time in types folder. So we tell it that use these types in order to communicate with the program. So the communication is basically easier because we know what instructions to or what instructions the program expects and so on. So, but now I would like to move to the test part or to this first case where we have on line 15 basically logic how to call the instruction or how to execute program. In this case, we are calling the initialize instruction. So we take the program, we take the methods field of the program, and then we call the initialize, and this .rpc actually tells that send the transaction. If we do not specify, then the transaction won't be sent. And then we have just a print statement of that will print the signature of the transaction. So let's now perform the anchor test. This anchor test command will actually perform the logic that is specified in the anchor.toml. So on the line 18, you can see that the anchor test will actually call this part. This means navigate to the test folder, take everything what is in the test folder. So that's why we have the stars here. And these files will be performed or will be called as tests. So let's call the anchor test. You can see that everything went basically correctly. The test passed, as mentioned also here, and we can see this green sign that it passed successfully, and we can see also signature. What might be kind of unfortunate right now is that you cannot see the signature on DevNet. However, we have other options, and that would be, for example, navigate to Anchor folder, and call Solana test validator. You just started a local validator. Take the signature. Now go to the Solana Explorer. Switch the cluster here to the custom. It will automatically set it to the local. And if we take the signature, let me zoom it in, you can see that we can actually inspect the transactions this way. So the transaction was successful, you can see the date where the transaction was called, and then basically this is interesting because as the program is unknown, then you cannot see what was called, but you can see that there is the program ID. So if I go back to the program, you can see that the program ID is same as here. So we invoked actually our program, and these are the program instruction data that were called. And as we do not have any accounts here, you can see that also there are no accounts in this part because the instruction did not expect any accounts. Now I would like to have hands-on example of the data accounts. So let's continue with the initialization of the data account. Let me make it more simple. So I will remove this part and also this part. Let me close the terminal. And let's just initialize simple data account and store some random data in it. So for that, first thing that we need to do is actually specify the signer. This signer will also pay the rent that will be stored in the data account, as I was discussing this in slides. In order for you to be able to store data in data accounts, you need to pay rent. So the balance cannot be zero in the data account. For now, the account is just signer, but you will see I will use anchor constraints to tell anchor that the account is going to be initialized, this is going to be the payer of the rent, and so on. So now let's specify the data account that we want to use. For that, this is the field called data account. As you can see, we defined signer with signer type. But how to actually define data account type? For that, we need to define additional struct. I selected name data account, but it can be whatever. So whatever. Second, we want to be able to use this type, to use this structure in the data field of the data account. So we need to specify account attribute macro. So this macro will derive required stuff. You can again Ctrl+Shift+P, expand, and you can see what it derives, but more advanced. And in this struct or in the data, I will refer it as data account. So in the data account, we would like to store, for example, some, let's store their string, okay? All right, so we will store actually string in the data account. Right now, we can fill this field. So in order to tell anchor that we are expecting data account of the whatever, as specified here, of the whatever type, you need to use account type with this lifetime, but what is more important is the inner type, what is whatever. That means currently it just expects data account with this whatever inner type. You may be asking, why do we have the lifetime? Again, this is more advanced stuff. Just remember that you need to specify this lifetime for the accounts. All right, I mentioned constraints. So anchor constraints, there are plenty. You can use these constraints in order to, for example, initialize data account. This data account, currently, as it is not initialized yet because we didn't call any initialize function yet or instruction, it is not initialized yet, okay? And we need to, or we want to tell in our program that once some user calls the initialize instruction, we want to initialize data account. For example, for him, the user will pay for it. And in this data account, we want to store the string with the field name hello. So to do that, using again additional macro, you can specify that you want to initialize the account. You can see if you hover over the initialize, payer must be provided when initializing an account. So if you would like to initialize the account, as I said, someone needs to pay rent for that account. So you need to specify the payer of the rent. In this case, we want signer to pay the rent, but it again shows error. So we hover over the init and you can see space must be provided with init. That means this space is the number of bytes that are going to be allocated for the data field in the account. So let's allocate 200 bytes. Why not? Lastly, a non-optional init constraint requires a non-optional system program. The logic actually, and this goes back also to the slides, as I said, the owner of the account can modify its data. By default, the empty accounts are owned by the system program. So when you would like to initialize new data account, you need to also include on this input the system program, because the system program is by default owner of this data account, as the account is not initialized yet. And the create account, or the instruction for initialization of the account, is one of the instructions that the system program supports. So apart from the transfer function that we were talking about, the system program also contains create account logic. So you can call system program create account instruction in order to initialize account. That's why we need to also include the system program here, because under the hood, the anchor will generate code that before actually this logic is performed, the account is initialized with the system program. Again, I will mention the Control Shift P. You can check how the account actually derives or generates code for these constraints, but this is again, from my point of view, more advanced stuff. Just remember, if you would like to initialize new account, as we do right now, you need to specify the system program. So it is called system program, and the type is really simple: program system. And maybe, yeah, I forgot the lifetime. All right. And lastly, the payer specified for an init constraint must be mutable. This is what I did not mention during the slides, but accounts on instruction inputs can be set as mutable and immutable. By default, the accounts are immutable, but we want to decrease balance of signer, as the signer is going to pay rent, so his balance is going to be decreased. So as we would like to decrease the balance, the account needs to be mutable in order for balance to change. So we want to change the field, so the account needs to be mutable. For that, Basically, the starting point is the same as for the data account, but we are not going to init or anything. We just mark it as mute. So this is everything from the source code of the smart contract. Sorry, not everything. We only specified the expected accounts. We also would like to store some particular string that is chosen by the user. So hopefully you will understand this better from the test perspective, but currently what we do is that after the context, we specify the additional parameters that we expect on the instruction input. That means apart from these accounts that we expect on the instruction inputs, we also expect this string type. And right now, I will leave this message here, but we would like to assign the hello string to the whatever or to the data account. We would like to store it in the data account. That means we initialize new variable called data account, which is mutable reference to the data account specified in the initialize context. Why mutable reference? This just tells that look at the account. This is mutable reference, so you can update the account, and that's basically everything. Then we can do hello. So we access the hello field and we take the hello from the input. And that's it. We took the account, in this case the data account. We can basically try to take also the signer, for example, but you can see signer does not have hello field. So we took the data account as a mutable reference. Then we take the data account, access the hello field, and in the hello field store the hello string input. Let me build this. All right, our local validator still runs. So let me clear and anchor build. And you can see the changes are already propagated. So from the test perspective, we said that we expect also the hello string on the instruction input. That's what you define here. So you can specify in this function, what do you input as a parameter to this function? These are the instruction inputs apart from or expect from the accounts. Except from accounts. If you want to include also accounts, you need to specify them here as additional accounts field or call, and then we've got signer and data account and system program. What is nice currently is that we do not need to specify all of the accounts because some of them can anchor resolve automatically. So for example, system program, but we need to specify the signer. For that case, we also need to create the signer account or signer wallet. Let's call it wallet because it will be wallet with some LAN ports. This is similar as your regular wallet where you hold Solana, for example. All right, that's for the signer. So we took anchor.web3.keeper.generate. So this will generate basically completely new Solana wallet with no data, no LAN ports, owned by the Solana program. The second thing, we need to also create the same stuff for the data account. So we need to create, or sorry, let's go back. We need to create empty wallet, and we are saying right now that in this empty wallet, initialize the desired space. The pair is going to be signer and the initialize, so that's why we have init here. That means previously the wallet is empty, but after this instruction, the wallet will actually not be empty, will contain some small amount of lampors in order to cover the rent fees, will also include the data space of 200 bytes, and will also include the string. But right now, let's generate it in this way. So now we can fill the accounts. So signer.public key, and also these two accounts. You can see we do not have errors here anymore because the system program was automatically resolved. But what we need to additionally specify is the signers field. I said that this account is going to sign the transaction because it is of type signer. It is expected as a signer of transaction. So this account needs to sign the transaction. But there is a bit catch, a small catch, sorry. This account, again, also needs to sign transaction in order to authorize that, yes, in this account, you can actually allocate space and create data. We can talk about why it is required. It is required because, for example, you have your regular Solana wallet and some of your friends decide that they want to prank you, so they create data in your wallet. That wouldn't be, or that would be possible if no signature is required. But when the signatures are required, your friends do not have possession of the private key, so they cannot actually sign the transaction, so they cannot actually create data or store data in your regular wallet. So that's why you need to actually authorize them, or you need to authorize the creation, the initialization. So as I said, signer needs to sign, and also data account needs to sign. Last thing that we need to actually perform is the airdrop. And why? On the line 11 and 12, we create two new wallets. For data account, it is alright because signer will pay rent into this data account with the during the initialization in our program. But the signer also needs to have some balance in order to be able to pay rent. So we need to specify the airdrop before we call the initialize function. So we can do program.provider.connection, and inside it, again, provider, and the request airdrop. Then we need to, in the request airdrop, we need to specify how much, the desired address where we want to airdrop, and then how much. So for example, let's airdrop him 100 Sol. There is no, like this, okay. Lamports per Sol. And give me a second, I have something wrong in here. Program provider connection. Oh, give me a second. I have confirm transaction. All right. And then we would like to also specify the commitment. So in this case, confirmed. This only means, as I was talking in the lesson 1, there is something like, I think it was called finalization. In this case, we would like to accept the confirmed finalization state. It is not, again, that important, but in order to work correctly, we want the airdrop transaction to be confirmed in order to perform the initialize. Because when we do not specify this constraint, the initialize instruction can be called when the airdrop is not done yet. That would mean the signer does not have airdrop funds yet. So that's why we need to specify this option. All right, and now let's call the anchor test. Something wrong happened. Insufficient lamp ports 0. Where do we airdrop? Signer public key. Maybe I will try to. Oh, wait a second, I need to evade it. It took a bit more time because I specified the finalized, but if you specify the confirmed, it should be. You can see that errors can occur, definitely. All right, it was faster this time. And yeah, you can see that there is the transaction signature. You can see that is initialized test name is marked as passing. And now let's investigate. So let's copy the signature. Let's navigate to the .anchor, or okay, we are already there. And let's call the Solana test validator. One thing I would like to point out here is that do not call anchor test while you run the Solana test validator, because probably it won't be possible. You cannot run both because the anchor test actually under the hood starts the Solana test validator. So it will show you error. So run one or another, but do not run them parallelly. Okay, let's start it. We can see it runs. Okay, we are correctly pointing to localhost, and you can see signature, which is our signature. This is the time, and the result of the transaction is success. And then again, there is the unknown program, but the program ID is the same. The instruction is again unknown because the cluster does not know what are the supported instructions in our program. But let's now have a quick look at the account inputs. So this first one is the transaction fee payer. You can see that the post balance is really huge. This account is automatically inserted by the anchor, so this account pays the transaction fees. But more importantly, you can see that there we have the data account, then we have the signer. You can see signer and writable. This data account was also signer and also writable, or I was saying it as mutable, not writable. You can see that the post balance is some small amount of Solana. This is because of rent coverage. And then we have the system program specified. And last but not least, this is the program that was called. All right, we went through this, but okay, let's have a look. So as we would say, this was the instruction input. So the first thing was the program that we invoked or executed. The second one, this is the address of the signer. As you can see here, it starts with H, and here it is also H, and here is the data account. So we will also inspect the data account later, but let's now continue. So under the hood, this call actually included more instructions. More precisely, it also included cross-program invocations, but this will be included in the part 2. But what was done actually was that in order to initialize the data account, the anchor automatically performed the system program create account instruction. You can see that the instruction contains from address, new address, the amount that needs to be transferred, and the allocation data size. So if I go back to the program, these are basically the inputs that I specified here. So we specified who is going to pay for the rent, what is the space that is going to be allocated, and we are about to initialize the account. So that's basically it. We are about to initialize the account or create the account. This is the payer. This is the account or the address of account where we would like to initialize the data in. This transfer amount is again automatically deducted by the anchor, and then this is the size. So you can see 200 bytes. And the assigned program ID, this is really important, as I was talking about the owners of accounts. So this new data account has its owner set to our program. And then what might be also really nice for you to see is that if we go back to the program, you can see that we've got this message macro printing greetings from and the program ID on the line 10. And that's what we can actually see here in the part of the program instruction logs. You can see that, maybe I will increase it a bit. You can see that program logged greetings from and the program ID. So you can also inspect program logs here. All right, and lastly, let's have a look at the contents of the data account. So again, I just clicked on the address. All right, so this is the address. The key pair was generated randomly, so completely random address. Balance is enough to cover rent exemption, that means 2 years of rent. Allocated data size 200 bytes, and the program and the account owner, which is ID of our program or our program. And you can see it is not executable. What I think it is not possible using this explorer is that we cannot see the data of accounts. But never mind. Let's navigate back to the test, and we will be able to see it from here. So let me copy this console log message. And also, I said last thing, but this will be also important for you to let me stop the validator. This will be also important for you to be able to fetch the data from the test site. So what we can do right now is to actually fetch the data from on-chain, or on-chain in this case from the local validator. Here needs to be fetch. So I just declared new variable. We are awaiting the how it's called, future, I think, in the TypeScript. Promise, sorry. We are awaiting the promise, and we are accessing a program account. Account is called whatever, or account type is whatever, and we perform the fetch method or function, and the argument of this function is public key of that account. So we generated this new key pair, and we take the public key of that account and we fetch it. What we can do later or right after, we can print the inputs. inputs, the contents. So let me run it once again. Voila, you can see that data account contains this field with the contents that we specified in the initialize instruction. So I think we are almost 1 hour in the video, or in the lesson, I mean in the hands-on example. I think I covered everything. For those who find anything like difficult, feel free to discuss it on Discord and ask questions in the dev help. Just maybe quick recap for you guys. Just remember, using this, you specify what data accounts you would like to create. In this context, or in this struct, let's call it struct, you specify what accounts are expected on instruction inputs. And in the module, which is marked with the attribute macro program, you specify all supported instructions by your program. Moreover, here are the instruction inputs. So we expect these accounts and we expect these data inputs for the instruction. All right, this was everything from this lesson. I hope that you learned something new. From my side, this is all about practice. So you need to basically, you can follow my steps. You can create the program by yourself as I did. But in order to learn better, or in order to learn more things, you need to play with it by yourself. And you also need to try to debug errors and issues and so on. If you need help, don't hesitate and ask on the Discord. And we definitely would like to help you. So yeah, that's everything from this hands-on example. And I would like to continue to the slides part again. All right, this was all from this lesson. Again, I understand that probably for some of you it was really difficult and a lot of new information, but don't give up. These are actually basics, but if you learn these basics and if you understand these basics, you can become a really great Solana developer, or even you can start auditor path. So yeah, try to understand the stuff that was described in the lesson. And what I mean by try to understand, definitely ping us on Discord if you need any help. And yeah, see you next week in the part 2 of the Solana programming model. Bye.